Welcome to the session on transforming code to Java 8. My name is Venkat Subramaniam. We're going to talk about what does it feel to really start writing code in Java 8, but more so, what if we're going to be taking code that exists and potentially write it or refactor it to something that looks like Java 8. I'm going to talk a little bit about what are some of the things we can expect when writing code in Java 8, and then I'm going to take 6 different examples, and we'll talk about each of the examples. Look at the code, run it, and then we'll start changing the code and then see where we end up with. Best time to ask questions or make comments is whenever you have it. So please don't wait till the end. Anytime is a great time for questions, comments, just about anything you want to talk about. And if you do have a question, I do hope that you have a question or a comment to make. And if you do, please draw my attention. If you raise your hand, I may not notice that you're raising your hand, even though I may be looking towards you. So either wave your hand, make a noise, just draw my attention. I'll be more than happy to listen to you. So let's get started. Well, the very first and foremost thing we're going to see is we're going to go from an imperative style of programming to more of a declarative and functional style of programming. If you have ever programmed for a long time in Java, C++, C#, or most of the other languages, you have been programming an imperative style of programming. Well, the world predominantly has been using imperative style of programming. And imperative style of programming is where we say what to do, but we also say how to do it. And when you code an imperative style, you get very detailed about every single step that you have to work on. I spent most of my life, I grew up programming imperative style, which tells you I had a terrible childhood. And I'm trying to really work hard to change that. So we all have been programming in imperative style. In declarative style and functional style, we tell what to do and not as much about how to do it. And as a result, we can focus more on getting our work done rather than getting dragged into the details. And in functional style, the very first thing is functional style is declarative. So what does that mean? Well, declarative means you focus on telling major high-level instructions and you let the underlying libraries take care of the details as to what to do. You work with higher order functions. What that means is, much like how you can pass objects to functions, you can pass functions to functions. Much like how you can create objects within functions, you can create functions within functions. Much like how you can return objects from functions, you can return functions from functions. So in other words, we can move around functions much like we've been moving around objects that comes from higher order functions. Which means not only can we do object composition, we can also do function composition, mix them together now. We honor immutability when it comes to writing functional style code. Well, when it comes to mutability, we modify variables, and that causes quite a number of problems in code. Understanding the code becomes more difficult. It's hard to maintain code, hard to errors go up when we have more mutability in code, and also concurrency is really hard with mutability. Well, functional programming recommends immutability, but also to deal with pure functions. Pure functions are functions with no side effects, which means when you call a function, it receives an input, and based on the input and only based on the input, it produces an output. It doesn't change anything while the code is running. It also doesn't depend on anything that may potentially change outside as well while the code is running. Well, the question is, why should we really care to program in this style when we are also used to programming in imperative style for so long? Well, the first reason is the code becomes a lot more concise to work with. And concise code absolutely is better. I don't think there's anybody here who wakes up in the morning to say, I want to go and write a lot more code today, right? In fact, this is one of the things I would call as experience. You find a person who is very young, just gets out of school, catch him on the way to work and say, what are you going to do? Where are you going? And the person says, I'm going to go to work and write a lot of code. And you catch the same person 15 years from now and ask the person, what are they going to do when they get to work? And the person says, I'm going to go remove a lot of code, right? That's called experience, right? We work towards writing less code, and the less code you write is better. Hands down, the code you don't write has fewer errors in it. The code becomes more expressive. It's easy to understand, easy to read, easy to maintain as well. And of course, you end up with a lot less code. Wait a minute, didn't we just say less code and concise code in one hand? Well, I'm going to say less code simply is fewer lines of code. But to me, there are 2 things that have fewer lines of code. One is concise code, and the other is a terse code. What's the difference? A terse code is a short piece of code that's waiting to hurt you when you least expect. A concise code is a short piece of code that's very transparent, easy to see, easy to understand. I want the code to be less and concise, not less and, of course, confusing. Now, it's easier to understand the code once we understand the syntax, the functional code that is. It's easy to modify, has fewer bugs in it for the reasons we talked about, and it's very effortless to parallelize and make the code efficient. Well, it's a lot of talking. Let's get down to some code and have some fun with it. So I want to talk about the very first example here, and I'm going to start with this code example. Of course, you never refactor code that doesn't work. Well, this code works in some fashion. Well, okay, what does this code really do? Let's take a look at this code, understand what it's doing, and talk about refactoring it to use Java 8 features. Well, I've got an executor service that I've started. I've got a new fixed thread pool on my hand. I've got a loop here, as you can see. And then I have a final int index. And then, of course, I have a submit method on the executor service I'm calling. And I'm calling a new runnable anonymous inner class, implementing the run method, sending this little piece of code to run in another thread. This one, of course, runs in the main thread. When I'm done, I'm shutting it down. So when I run this code, you can see it's producing that result. And because of concurrency, you can notice every time I run it, the sequence is different to the true nature of concurrency. Obviously, it's going to move things around a little bit. Great. But let's look at the code and understand a few different parts in this code and see what we can maybe change or do a little differently. The very first question I'm going to ask you is, what in the world is that final? Why are we putting final in this case? I'll tell you the answer why we are putting final, because most programmers will tell you the reason I'm going to say. We put final here because the Java compiler threatens to come burn our village if we don't, right? So the point is, we put final because the compiler endlessly complains. You're like, fine, are you happy now? Here you have it. So we kind of put it because the language compiler complains about it. But in fact, what I really want to do is, I want to use this variable I right here in this code. But I couldn't do it. Why? Because unfortunately, I is a mutable variable in the loop in Java. How sad that really is, right? It's a mutable variable in the loop, and because it's a mutable variable, I cannot use I, so I created this temporary variable. In fact, this is usually a garbage variable, and you don't normally give it a respectable name like index. You call it t or temp because it doesn't deserve to exist, right? So you provide this variable, put it as a temp, and then you pass it down here. But unfortunately, though, the reason why we had to put final is to really preserve the copy semantics. In other words, we have this little anonymous inner object that's going to float away, but the variable is on the stack. Well, when the object floats away, and then once the object goes away, the life of object could be longer than the life of this particular stack. And how do you deal with this object being gone from memory when you need it up here? Hey, there's a way to fix it. We can make a copy of it. Hey, that sounds like a great idea, but if I make a copy of the object and then change it, well, that can be very confusing, not to the compiler, but to us, the programmers. And then we're not sure, did we copy before the change, did we copy after the change, or even better, are we copying during the change? Well, to fix all of that problem, we said, fine, make it final, and be done with it. Well, okay, we did all of that, but this is not Java 7. This is Java 8. So notice what I'm going to do. I'm going to quietly remove the word final. So I got rid of the word final. I run the code, and notice the code still works. Hey, how is that? How come I don't have to put the word final? Well, Java 8 says, you and I have been going out for 20 years. I'll trust you just a little bit. So the point is, the code says, as long as you know what you're doing, you don't have to put the word final. So notice, I did not mark it final, and life is really good. But what if I come along quietly, and I say index equals 22? Now the compiler clearly gives an error. It says, I thought we had an understanding between us, right? So the point is, it says, you don't go around and start sneaking around and modifying variables. You are supposed to treat it as final, and that is called effectively final. So in Java 8, you don't have to mark variables final as long as you treat it like it is final. So that's called effectively final, and that removes that ceremony, and the compiler kind of guards you and says, if you try to modify it, I'll give you an error. If you don't modify it, we're just good. So that is effectively final. That's great. But then if you look at the code a little bit further down, what are we doing? Notice we are creating a runnable. That's a ceremony. That's a noise. We can remove some of this noise in the code. So I'm going to remove this and replace it with a lambda expression. So I'm highlighting the part of the ceremony, remove it. Put a little arrow right there, and I'm removing the rest of the ceremony in this code, and you can see the code is still working. So rather than using an anonymous inner class, we replaced it with a lambda expression, and that was quite happy, as you can see right there. Well, that's great, but that index is still a stupid name. Can I just not use the variable directly? Well, the problem in this case is this for loop really is modifying I repeatedly, and so we cannot really do that. But there is a good news. What are we really doing with this loop? Well, for every element we want to do something, well, there's actually a better way to convey that intent in Java 8. And before I talk about that intent, I'll talk about something else, and I'll come back to this. Actually, you know what? Let's do this. Let's communicate that intent, and then we'll refactor one more time. So java.util.stream.star. So I'm bringing in the stream package in here. And I'm going to say int stream.range, and I'm going to go from the value of 0 up to a 10, so that will go from 0 through 9. And you can use this range function to communicate your intent. And then I'm going to say, in this case, a dot for each, and given an index value that I have received on my hand, let's actually say I for a minute. We'll come back to that. And I'm going to now put a little block of code. We're going to refactor this in just a minute. And I'm going to take the guts of this loop from here and move it in here and get rid of the for loop right there. So notice in this case, we used a for each. And for every element in the range, I want to perform an operation of performing that particular value. Well, that's a bit of a refactoring, but we gained something a little bit more than just using lambdas here. If you notice this variable I, that is a parameter coming into this lambda expression. Well, if I were to call a function foo and send a value 2 to it, and call foo and send a value 4, now if foo was, let's say, a function right here, let's say this function was up here called, let's say, foo, and let's say int a is the parameter. Now, when you call foo with a 2 and a 4, you would never say a was a value 2 and it was changed to a value of 4. You would never say that. What you would say is the first time foo was called, the parameter was a. The second time foo was called, the parameter, which is a different instance, is a value of 4. So you know clearly it is not a mutation of the variable, but a rebirth of a variable every time you call this. Well, that's exactly the same concept you are using when it comes to lambda expressions, because lambda expressions are nothing but anonymous functions. So you're calling that function twice, thrice, 4 times. That I is a brand new variable every time rather than a variable being mutated. And as a result, I can get rid of that index from here and replace this with the I, because I is not a mutable variable. It's perfectly safe to use it. And I removed that garbage variable called index. Now that we removed it, we can gain a little bit further from here. I don't need that bit of a ceremony in the very end over here also. So what we can do here is we can remove some of this noise from this code as well, and we are able to refactor this code. So you can see in this case what we did is we took that a bit of a verbose code and we rewrote it, first of all, using a range function, which is part of the JDK 8. We used an internal iterator rather than using the external iterator. We used lambda expressions to communicate the intent of passing these anonymous functions around. And we can also see that we have a lot more concise and less code than we did before. You're looking at about 40 to 50% weight reduction in Java code when you start moving from Java 7 to Java 8. And that's what you're seeing here in this particular example. So we used a few APIs available in Java 8, and we were able to build up on top of that. And that's basically what we learned in this particular exercise. So we are using the single abstract method interfaces, but they are also called as functional interfaces. I always chuckle when I say the word functional interface because it makes me wonder if some interfaces are functional, then are the others dysfunctional? But in any case, there are functional interfaces now in Java 8, and we can pass lambdas anywhere these functional interfaces are expected. Any questions or comments before I move from this particular example? All right then, so let's talk about the next one. I want to use iterators, but let's look at a slightly different example of this iterator just to gain a bit of understanding of what's going on here. Notice this is called isPrime function, and as the name indicates, it's going to tell you whether a given number is prime or not. Well, that's great. And what does this code do? This is a beautiful piece of code, as you will realize. It is doing a while loop. It goes through and square root of first 100 primes. That thankfully, that name gave us an idea what this code is doing. If we write code like a lot of people write, I would have called it S, and you would have no clue what this code is doing, right? So this tells you a little bit about what this code is doing, square root of first 100 primes, and then a while loop to do this stuff, and then we print the value down below. So let's run this code and see, yeah, that's giving us some result. But let's get back and start looking at refactoring this code. This is a full-blown imperative style code. We're doing every single thing by ourselves. But let's take one step at a time. Let's attack the isPrime function. Now, this clearly is an imperative code. What are we doing in this code? We set a variable, first of all, to false. We loop through using the external iterator. We are checking for a value number. We're changing a little variable and something we normally do. But what is that called? Well, we all know what this is called. It's called a flag. Anybody likes using flags? Nobody does. We all hate flags. In fact, flags are the lowest life form you can ever find. In fact, we hate them so much, we even misspell them when we define them, right? So that's a flag, and we don't really like them, and they kind of really make us feel really bad when you write the code, but we still rewrite the code with it. Well, let's see if we can write this code a little bit better than this. So notice what I'm going to do here. I'm going to just comment this out so we can compare and contrast it. So I'm going to say return number is greater than 1 and, but notice what I'm going to bring in here. I'm going to bring in our friend, the intostream, one more time. So intostream has the range function. We saw that already. So I'm going to say intostream.range. So I'm calling the range function, as you can see right here. And then what is the range I want? Well, look at the for loop. The range is 2 to number minus 1. Well, range skips the last value anyways. And then I can say dot none match, and given an index I, number mod I is equal to 0. So notice all that code we wrote up there has been replaced by that very nice, concise code, which is very highly expressive. So we went to the intostream, called the range function on it, and then we said for all the range of value, tell me none of the value in the range matches this expectation or divisibility, and we wrote the code very expressive. So as a result, we are not sitting there and writing code at a very low level detail. We are being very expressive in what we are doing with the code, and that becomes a lot more easier for us to get our work done as well. And it feels like we are communicating more intelligently than being at a very low level that we did a few minutes ago. So that's basically the intostream coming to work one more time. Well, let's get back to this code for a minute. And this is actually a lot more worse than we had in the above code. What are we doing with this code? We're using a while loop, and we're saying while index is less than 100 and doing all this work. Let's examine this code just for a minute. We are first creating an empty collection. You can see that's actually a very tedious operation because we had to spell out the silly detail to say, please wipe and clean and be ready, right? These kinds of low-level instruction we end up giving. Then comes this beautiful thing called index equals 1. You kind of look at this and say, I don't know why I'm creating it, but it's there. And then comes this most wonderful less than 100. How many times have you looked at that and you have said to yourself, is it less than or less than or equal to? You better ask the question every single day. And the day you don't ask it is called the off by 1 day error, right? And that's very annoying when that happens. And so we all suffer through this. And then comes the if statement, and my most favorite is this index plus plus. Because if you don't put it, you get what's called nirvana, right? This keeps running forever. And then you're like, why doesn't this quit? And even better, put it inside of this to have more fun. So you better keep it exactly at the right place. So in other words, I would argue this is one complex piece of code. Hey, wait a minute, why would you say it's complex? Isn't it simple? No, it's not simple, it is familiar. And we get confused all the time between these two words, the word familiar and the word simple. The word simple means something entirely different. The word familiar means I've seen it many times, I don't care to see it again. Like the word familiar, like my in-laws, very familiar, but I would never use the word simple when it comes to them, right? So the point really is that it's very familiar piece of code, not a simple piece of code. And it's complex because you got to put things in the right place, easy to make errors, easy to fail, and you definitely don't want to get there. Well, can we do this better? Oh yeah, we can definitely do better. But before we do that, let's look at one other concept. I want to get back to one other class we can bring in, which is called the stream class. Now, the stream is an awesome little piece of class. It does a lot of things, but we're going to do one thing with it for now. And what I'm going to do right now is I'm going to comment this code out, and then we will come back and look at this after we refactor it, and then see how this is going to work. So for now, I'm going to just go ahead and put this one here. We'll come back and refactor this. So what I'm going to do here is simply say, here is my list of numbers. We'll come back to that. But I'm going to say stream.iterate, and I want to start with what? Well, remember, index equals 1. So I'm going to say 1 comma, given an element, element plus 1, just stare at that for a minute. Now, what does this say? This is actually a iterator, but it is creating what's called an infinite series. Well, the series is absolutely infinite. It starts with 1, and then there is 2, 3, 4, 5. We can keep going forever. Now, the first thought that comes to your mind is, oh my gosh, if it's infinite, where would you store it? On the cloud, of course. So the point really is, so this is infinite in size, absolutely, and as a result, it doesn't have any bounds at all. But it's very clever, though. It is not going to produce any values for you until, of course, you ask for the values. So it's extremely lazy. No, you don't need that cloud I mentioned. So the point is it's very lazy evaluation, and so it's going to really create values on demand. If you're wondering how this actually works, you've probably seen these kinds of collections quite often. You probably go to a very busy office, like a driver's license office, and you realize there's a lot of people waiting, and in the corner they have this little ticket machine. You know what I'm talking about, right? And you go there and you pluck, and it's like, oh, 287. Oh boy, that's going to be a long wait. And the next person comes and takes pluck, hey, it's 288, and the next person 289, right? If you ever doubt this is not an infinite stream, take a kid with you. You will know this right away, right? So the point really is that can keep on giving, but only on demand, and you can ask for values. This is exactly what this code is doing. Well, that's great so far, but what do I do with it? I'm going to say dot filter, and what am I going to do with this filter? I'm going to say, given an element, tell me it's a prime value. So notice how we are only filtering prime values. So we went from an infinite stream to an infinite stream of prime numbers. Well, that's great so far, but I really wanted not just the prime values, but I really wanted the square root of the prime. So math square root, and now we have an infinite stream of square root of prime numbers. Now, of course, that's a little nerve-wracking because it's an infinite stream of square root of prime numbers, but be satisfied, it's all lazy, no work has been done yet. Well, then what do I want to do? The next thing I'm going to call is the dot limit on 100. Did you notice one thing? It's not less than 100. It's not less than or equal to 100. It's 100, damn it, right? So there's no confusion about it, right? So you don't have to waste your time sitting there and scratching your head. It's as simple as that. You're done with 100. That's extremely expressive, as you can see. Well, now that we have said, I want 100 of the square root of prime values starting from 1, and bingo, we have what the result we want. Well, one last step after this, we're going to do a dot collect, and we're going to ask for a toList from this, and we're going to grab that list and store it into this list object that we have on our hand, so we can simply put that back into that collection. But of course, for this, I need to bring in one more import, and I'm going to bring in over here the java.util.stream.collectors.toList, which happens to be a static method I'm going to bring in from that library. So as a result, we brought in the toList method, which is the collectors.toList. And as a result, we went from an infinite stream of numbers 1 forward down to only getting the prime numbers, down to only the square root of the prime numbers, but 100 of them packed into a list, and that's what we are doing in this particular case, and we got exactly the same result. Now, there are a couple of different observations you see up here. The very first thing is, notice what we did here in this code and in the previous code. We used a for loop and we used a while loop. Now, most of our Java code is filled every corner you turn with a for loop or a while loop, right? We see this every single place. And what happens? Every time you look at this code, you realize every corner you turn, we keep using for. Hey, I want to loop through all the values. What do? A for. I want to skip a few values. What do? For, if, continue. I want to take a few values and skip again. For, if, continue, and break. Now, this begins to feel like this, right? You hear a knock on the door. You open the door. There's a guy with a hammer. You say, who are you? He says, I'm here to fix your kitchen. You say, well, okay, but you don't seem to have anything other than a hammer. And the guy takes a whack at the door and says, I don't need any sticking tool, I got a hammer, right? You probably let him in and run out and call the cops, right? So the point really is, that's how it feels when you code in Java with all the for loops. On the other hand, what do you expect? The doorbell rings, you see a guy with a little bag of tools. He says, here is there to fix the kitchen, you let him in. He comes to the kitchen, puts on the floor, and puts all the tools out to get ready to work. You look at, hey, there's a hammer, but there's a chisel, there's a screwdriver, there is a little wrench. And you look at all this and say, hey, there's nice little tools. He says, oh yeah, these are my tools for my job. And you ask him, are you going to use all of these tools? And he laughs and says, no, I'm not going to use all of these tools. The person who uses all the tools is called a consultant. But I'm going to only use the tools that actually make sense, right? So the point really is, you have these little tools to use, and now you have a little iterate tool, a little filter tool, a little map tool, a little limit tool. And you can see how we are putting together with these combination of tools as they make sense, rather than simply saying, I'm going to use a for hammer for everything or a while hammer. Well, that becomes a lot more effective to write the code. And the second thing you notice here is something very phenomenal. If you look at this code, in fact, I would challenge you to do this. Put this code on the screen, but sit opposite to the person looking at the code and have them ask them, what does this code do? And you will watch their eyeball movement, and it'll go like this, right? Because they're going up and down in the loop, and then eventually it'll come down asymptotically to that point. That point is called the point of confusion, right? Because like, what does this do? But on the other hand, if you look at this code, notice how it's a single pass through the code. Here's a collection of all the numbers. I want only the prime. I want their square root, but I want 100 of them. I put them in a list. Next question. So you can see how the code reads like the problem statement. So in other words, to me, this is very important. A good code is like a story, not like a puzzle. So if you look at the code in the top, that code is like a puzzle. If you're sitting next to a business analyst, and the business analyst, you know how they are, right? The business analyst looks at this and says, hey, what does this code do? And you're going to say, that's what I'm trying to figure out, be quiet, right? So, but a lot of times, when you look at the code in the bottom, you can have a conversation with them and say, that's what I'm doing, dude. Does it make sense? Do you want anything else? So a good code is like a story, not like a puzzle. But what happens when you write puzzles? When you write puzzle, your coworkers don't have a clue what your code is doing. They're looking at the code, they're staring at it, and they're spending hours scratching their head. And at the end, you can see the change in their face because they finally figured out your clue. But remember one thing, the minute they discover the puzzle you created, you think they're going to be quiet? They're going to come back with vengeance to place the next puzzle for you. In the meantime, we got production code to be released, and that's not going to happen. So it's very important for the code to be expressive and readable and maintainable, then turn into a puzzle. And that's one of the things I see here in the code that we saw with the functional style, is that it's very expressive, easy to see how this is working, and as a result, we can just follow along very nicely. So what we have done here is we started with this collection, and we went through the iteration of all the values, cherry-picked the values we are interested in from the infinite series, transformed them into a square root of the values, limited the size of it, and then, of course, stuff it back into a list, and we were done with it. And that's basically what we did in this example. So what we did here is we used internal iterators rather than using external iterators. We used very specialized functions, not just a hammer, but chisels and screwdrivers as well. We used function composition. This is a convention in Java 8. Notice how these dots are vertically lined up. up. So that gives us a nice way to see the flow of transformation through the code, and we do this quite often. We made use of infinite streams, and we also employed lazy evaluation. You cannot have infinite streams without lazy evaluation. You cannot have lazy evaluation without purity of functions. You cannot have purity of functions without immutability. And you can see how all these things beautifully line up together. We want to emphasize immutability not because it's a fashionable thing to do. Immutability paves the way for writing pure functions or functions with no side effects. The minute we write functions with no side effects, we can then be lazy about evaluating them because there is no side effect. It doesn't matter whether we run it now, run it later, or never run it at all if the result doesn't matter. And the minute we can have lazy evaluation, we can then engage into infinite series. So all these really build up to greater good in functional programming. So very powerful series of concepts that paves the way for something beautifully ahead of us. Any questions or comments before we move forward from here? Please. Which part is? Got you, got you. Excellent. So, very, very good question. So, let's step back for a second. There are two kinds of functions with streams. Those are called intermediate functions and terminal functions. Intermediate functions are functions that are not going to do any work, but they just accumulate, or what is called fusion. So to understand that, thanks for asking the question, let's comment this out for a minute. We'll come back to this in a minute. So I'm going to go back to this code, and I'm going to do something a little silly here. So let's get rid of this code right here. And I'm going to put a little comment, a line here. So I'm going to say in here, called. That's all I'm going to do. So if I go back and run this code, you can see that in this, did I say console? Sorry, writing too much JavaScript lately. Okay, so I want to go back here, and you didn't see me do that. Okay, so in this case, I'm going to say called. And if I run this code, you can see, you saw all these called being called. Well, that's great. Now let's go back and remove that as well, and we'll just run through that. You can see that happen again. Well, these are called intermediate functions. Well, collect and functions like that are called terminal functions. So if I were to stop shy of 1 and remove the collect and run the code, you can see it produced no result at all, even though I called all those functions. Just to see that really happening, pardon me, if I go back here and say done for a minute, you can see that in this case it did all of that. But if I stop 1 shy of that, you can see it calls done, it never executed it. So in other words, these are the terminal functions that actually trigger the computation, and until you trigger the terminal function, it doesn't do any work. Now, not only is filter and map lazy, even limit is lazy. That's cool, how cool it is. Limit says, if I see 100 values walk by, I will stop, but guess what? I did not see 100 values walk by. I'm not going to do any work right now. So it's very lazy as a result as well. So that's what's happening. Any other questions or comments? A little louder, please. The question is, can you do them in any order? The short answer for that is yes. But the order has to make sense logically for the problem on hand. So usually the algorithm should really produce the right result. And yes, you can change the order depending on how the value is produced. You can also parallelize this if it makes sense. But usually laziness and parallelization don't go hand in hand. So you normally pick laziness or parallelization. And of course, if you go parallel, you can easily change the order much more easily than when you do it sequentially. So it depends on the problem to see if the result is correct. Very good. So let's, so let's continue further. Well, one other thing we normally do is violate this thing called tell, don't ask principle. And we end up really violating this quite often in code. So let's look at one example here. Let's say we have a class called a time slot, and the time slot here, I've just hacked up this code. It's a random that's going to be, there's a schedule that's going to schedule a time slot. I commented out the code. Is available tells me whether the time slot is available or not. Well, then comes the array of time slot. So there are a bunch of time slots. Some of them may be available, some may not be available. We don't know. But I want to find the first available time slot. Remember, nothing may be available. But I loop through one at a time. I check if a time slot is available. If it's available, I schedule it. And if it's not available, I skip to the next one. If it is available, I schedule it. I assign the first time slot variable, and I call a break. Very common imperative style of code we all used to see. Of course, when I run this, if it found a time slot, it gives me. If not, it gives me a null. Well, unfortunately, if it gives me a null, I may bomb on it if I access a method on it, so I got to do an explicit null check. But often I forget to do a null check, and the program really sucks after that, but we can fix it by being a little cautious. Wouldn't it be nice if we get a compile time error rather than runtime error if there is a potential null on our hand? Well, let's see how we're going to rewrite this code. So what I'm going to do here is, I'm going to say, first of all, time slots. So I'm going to say time slots dot stream. So notice I start with the stream on my hand, and then I'm going to say a dot filter. And in this case, I'm going to say time slot is available. So if you stare at this code for a second, notice this is going to check and only cherry pick those time slots that are available. But if you look at this code through your human eye, you're probably going to freak out because this is going to check every time slot that's available, but you really wanted to check only the first time slot that is available and keep marching until you find that first one. Well, remember though, streams are lazy. So streams don't eagerly evaluate this. This is available will be evaluated only as many times minimally as needed. We don't know the answer, how many yet, because that is specified downstream. That's why it's a little counterintuitive. The action that's performed upstream is actually based on action performed downstream that ripples up to say what you want to do. And the reason is it doesn't take the collection and run through the collection through an operation. Instead, it takes one element, runs that one element through multiple operations, and only then takes the next element and runs it through multiple operations. So in other words, it doesn't take the collection and walk every row. Instead, it takes one element and walks every row top to down, and then starts with the second element. So it's a very different execution model compared to what our human eyes show us. It's not what you see that you get. It's something very better and different that you get out of this. Now that we got through this, I'm going to say dot find first. And the find first says, find me the first one that is available. And as a result, the minute it finds something that's available, it's going to give us that. Well, what if something is not available at all? What is it going to do? Well, to understand that, let's look at the output of this, and that will reveal immediately. Notice it says optional time slot. Well, what is optional? Optional is a value may or may not exist. So if you're not sure some value may or may not exist, don't return a null if it doesn't exist. Instead, return an optional. If the value exists, it contains an optional of that. If the value doesn't exist, it gets an optional empty. Well, that begs the question, how do you get the value out of the optional? Well, you can go to this and say, well, this is the object I'm getting, so I'm going to say optional of time slot. And once I get the value, we'll say first value, for example. Well, of course, it may or may not exist. We don't know that. So there are several functions you can call. One of them is you can say first value over here. So let's say first value dot if is present. And you can query it. And if it is present, you can say first value dot get and get the value. That's one way you can get the value out of it. Alternately, what you can do is, you can also say or else, and you can provide an alternate value to use if the value were not available, and you could do that also potentially. So you can call some of these different functions as it may make sense. Well, in this particular example, you can also call a get, but you should never call a get without a present. That's not that much fun to do. So now that I'm going to use this particular function, I'm going to say time slot, let's say first value equals, and I'm going to say in this case or else, maybe new time slot I can create if there's not one available. That's a business logic. I can use it any way I want to, and I can make a decision after that based on what I want to do. So if I do this in this case, this is the first value. I'm going to change this to first value. You can see that's still working, but look at the difference in code. This was a code with a null, and we know null is a smell. but we don't have any null in this code. It's a lot more civil, as you can see when you write this code. It also prompts you to really check for the null condition, meaning if a value doesn't exist, and you make a very clear decision at the end of the find first to do whatever you want to do. And again, this uses lazy evaluation under the hood, and that's basically how we are writing this code. So the code becomes a lot more transparent. It's easier to understand what's going on once we understand the semantics of the code, of course. We're avoiding the smell of null, and we also used optional as well, so that becomes a lot more easier to work with. Any questions or comments before we move on from this one? Please. That's a great question. How challenging is it to debug this particular code? I don't know, because I don't spend time writing bugs to debug them. So, so that's a really good question, but I want to come back to that question with a slight difference. So step back for a minute. Ignore this for a second. Let's say I come to you and say, pardon, I apologize for the volume here. So suppose I come to you and say, how hard is it to debug Java code? You're going to immediately tell me, oh, it's very easy to debug Java code. I do this all the time. I say, okay, gosh, that's really good to know, because I got a lot of threads on my hand. You're like, get out of here. The minute you bring multi-threading, the devil walks in, right? So the point really is, what makes Java code hard to debug is not Java code, but it's the non-determinism of multi-threading. So what makes this code hard to debug is not lambda expressions. You can step into lambdas and debug like the way we normally debug. What becomes a challenge in this code is really the lazy evaluation. So to answer that question, let's come back to this for a second. Let's say for a minute, we have our little code, and let's say, this is why we have to be a bit careful about certain things we do. So let's say we have a list of numbers, all these numbers on our hand. Well, what I want to do is I want to say, in this case, let's say int factor equals 2, and I want to say numbers.stream, and I'm going to say .map, and I'm going to say given an element times factor. Well, this part is so easy so far. I'm going to say stream, and I'm going to say integer, and I'll just say assign it to this for a minute, and let's say that's all the code we have so far. Well, then what I'm going to do is I'm going to come back here and say stream dot for each, and I'll say system dot out and print line this particular code. So if I run through this code, well, I need a stream, so let's bring in the stream. So in this case, of course, you can see that this particular code produces the desired result, no problem. But here comes the charm. Well, notice this factor. I mentioned this earlier. I mentioned that factor is effectively final. So what Java tells you is, if I say factor equals 44, Java says, you're out of your mind, you shouldn't do this, right? Now, I want to emphasize one thing, and thanks for your question, because this also brings another thing we should be very careful about. Well, you know how some Java programmers never take no for an answer? So this programmer can say, oh, really, Java, you won't let me do this, huh? And so I've seen Java programmers say, go back and say new int, and then you can put a 2 right here, right? Well, now, if I go back to this code, this is going to become a factor 0, obviously, right here. And notice at this point, that seems to work. But what if I really say factor 0 is equal to 44? Well, look at this code for a minute. We did the multiplication right here, and then we changed the factor. Well, the very first question is, will Java complain? The answer to that is, Java no longer complains. Well, you may ask me, well, what does Java do then? Well, Java gets together, all the Java VMs get together in the night, and they laugh at us if you write code like this, right? That's what they do. Because it's like, I told you don't do it, and you got around me, right? But then the question is, what's going to be the output of this code? Is it going to be double the value or times 44? Take a wild guess. Times 44, as you can see. Well, that's because of lazy evaluation. So to go back to your question, if I put a breakpoint right here, that breakpoint will hit, but it will not hit when I go through that line of code. It'll hit when I come here, because that computation is triggered by a terminal function, going back to this question earlier, and not by an intermediate function. So to answer your question, we have to first learn the semantics of the language, and the semantics of the language has evolved. But once you understand the semantics, when you put the breakpoint, you're going to nod and say, I got it, I know what's going on here. It won't stop then, it'll stop further down, and then debugging becomes easier. So we have to really understand the semantics before we can debug, otherwise it becomes very frustrating. Very good. So we looked at how this can behave. Let's talk about one other example. Well, this example, I'm going to write code here to talk about this. Let's say for a minute, we have a piece of code. I'm sure everybody here has seen this piece of code before. Let's say we have a file I want to use. So I'm going to say java dot, let's say io dot star. Well, I want to say file, and I'm going to say dir equals new file, and I'm going to bring up, let's say, the current directory itself. So in this case, I've got the current directory. I'm going to say output dir and run this code. Well, okay, that was very helpful, dot. Okay, great. So now I want to get all the children in this directory. So what would I do? I'll say file square bracket children equals, and I'm going to say dir dot list files, and that gives me all the children in this directory. Great. If children is not equal to null, I want to do some work. Well, what work am I doing? Well, let's say the work I want to do is print the names of all the files in uppercase, but comma separated. So simple, right? Names in uppercase, comma separated. Well, let's give it a try. I'm sure everybody has done this, right? So what would I do? Well, I could say, for example, well, I've got the children, so for file child, and this is going to become in children. Well, that's great. I got to get the name of the file, obviously. So I will say child.getName.to uppercase. Well, so we could print it in uppercase. Great. You can see that all printed nicely. Well, okay, that was cool. But wait a minute. Was it in uppercase? Yes, it was. But it was not comma separated. Oh, of course, we can do that. So a plus a comma. So now it'll be comma separated, isn't it? Well, we can certainly do that. So we can get those files in comma separated. I'm going to see if there's another directory I can use over here. So actually, let's go ahead and create a dir here. How about that? So I'm going to touch two files, f1.txt and f2.txt. So it's easier to see this. So I got a directory called dir. So let's go ahead and say users, and let's say temp dir, and that's what I want to get out of this. So run that. Hey, that's cool. But wait a minute, they're not on the same line. Oh, we can fix that too. We can do that, and of course, at the end, we can do a print line of nothing, right? So run it. Wonderful. Oh, wait a minute, though. There's a comma, a stupid comma in the end. Anybody have seen that problem before? Yeah, we all have, right? And how did you feel that night? Terrible, right? Terrible. Because you said, how do I get rid of that comma? And I'm sure some of you came up with this beautiful, beautiful algorithm. That's called put that comma in and remove it. And that didn't go very well because string is immutable. Oh, darn it, I could go for a string builder, string buffer, and you're struggling with all of that. And after about 30 minutes, you realize, gosh, how did you not realize that there is such a simple answer to this? And I always like simple answers. What is the simple answer? For int I equal to 0, I less than children dot length. Oh, wait, it's not length. Is it size? Is it count? Is it length? Is it... Anybody knows? Size, but it's an array though, length. Okay. And then I plus plus, right? And, oh, but is it less than or equal to? Remember that wonderful thing? Of course we go, less than, are you sure? Well, okay, we're sure right now. And then what do? I'm going to output children.get. Oh, it's not get, it's square bracket I, dot get name, and then dot to uppercase. Okay, we got that part now. Run the code. Hey, but where's the comma? Still not there. Oh, of course, remove that. And then plus a comma. Well, not quite, because there's still the comma in the end. Okay, I've got to fix that. So print without the comma, got it. And then you say if I is not equal to children.length. How do you feel? And then not equal to, it's like, is it -1 over here? And when you're done with all of that, you're in disbelief, right? God, this cannot be happening to me, right? Well, so you can kind of feel the plight of that. We've all been through that. Let's try this one more time. Well, a lot of different languages provide constructs to do this. I've used a function in Groovy called join, make string in Scala, and str in Clojure. So obviously, Java needs to have one as well. Well, thankfully, we can do this really well. So let's bring in a few helpers here. So I'm going to say util.stream.collectors.star, and I'm going to bring in a static import into collectors. We saw collectors a few minutes ago. So now what am I going to do? What I'm going to do now is I'm going to say, well, we got the children, stream.off. Well, I need to bring the stream then. So let's bring in the stream. Okay, great. Stream.off. Well, earlier you saw I could take a collection and call a stream on it. Well, this one is not a collection, it's an array. So I got to say stream of children. And then, of course, I'm going to say dot. And now that I have a stream of these files, I can now say a map. And I will say file get name is the function I want to call. Then I'm going to say on this a map of string to uppercase. I'm doing multiple transformations on this particular call. Well, then I say collect, and then I'm going to collect this, but I want to print it out as soon as I collect it. Why not? So I'm going to collect it and print it. So that's going to be the very end of it. But collect what? Joining with a comma. So when I run this code, notice how it did a comma, but there's no comma in either end of it. Well, the day I learned about joining, I cried that night, right? This is the way it should be, right? Programming should be this easy. So that's a very high level of abstraction, as you can see. So you can do joining. Joining could be anything you want to join with. Could be a class path separator that you want to join with class path. Whatever the context may be, it's up to you. So that gives you the ability. Well, the joining actually uses a function on the string class internally. So if you have a string on your hand, you can use functions on it directly as well, and you can make use of this kind of behavior, and with immutability, of course. And that's what you're seeing in this case. You're able to join them together, and that works really nicely, as you can see. Well, great. Now we saw quite a few things, but I want to get to a slightly different example here. And the example I want to look at here is going to be this one here. So let's say we have a list of person, and you can see it's a list of 4 people, Sarah, Mark, Bob, and Jill. And I call the sort method on it, and then I print the result out of it. So you can see that it's printing based on some kind of sorting. Well, the first question is, what does the person class have? So let's look at the person class, and you can see in the person class, we have a comparable on the top. We got a name and age, a constructor that initializes them, getters and setters, and toString method to print it, and a compare to method that's comparing on the age. So that's basically what we have here. Well, my first question is the sort function. What can you say? Sort is good, bad, or pure evil? What do you think? It's evil. I agree with you. Can't be any more true. It's very, very evil. Now, the first question is, you may say, if it's evil, why did they do it? Well, I'll tell you why they did it. They were young and they needed the money, right? I mean, really think about this for a minute. What did Java compete with 20 years ago? 20 years ago was a very dark time. Some of you are probably very young. Thank yourselves for that. You didn't grow up during that really bad time. But the rest of us had to really grow up during that time. It was really bad time because we had 2 things going for us. We got excited because we could do applets in Java. I'm really sorry. This is shame we would have to deal with every single day, right? We got excited because we could do applets. And we had to compete with C++. And C++, what was C++? I don't know how to describe it. C++, well, it was just what it was, right? And there was no morality. There was no ethics. They got the result they wanted. It didn't matter it was correct. It meant only it was fast. So Java had to compete with this language, right, and produce the results. And so you had to really get the performance through any means you can. And so, of course, we had to do mutable things and evil things. Well, it doesn't appear to be such a great idea today as it did 20 years ago, but still we had to do that. Well, there are 2 reasons why I don't like it. The first reason is, notice that this is mutating an input parameter. Well, mutating parameters given to a function should be punishable under law, right? Nobody should ever write code that changes an input. Now, this causes unnecessary defensive mechanism. You start cloning objects before you pass them if you know this is going to happen. That's pure evil. The second thing is, if you look at the person class, it is actually very intrusive. You had to walk into this class and implement comparable, and I'm not too happy with it. So I'm going to get rid of that. So no more comparable on the person, and I'm going to remove the compare to function as well. Of course, this code is completely broken now. I cannot use it, but good enough. I can't really mess with the person. I want to do this a little differently. So how can I really perform a comparison and get the results out of it? Well, let's give it a try. So there are a couple of interesting things I'm going to use here to make our lives easier. The first thing I'm going to do is I'm not going to change the people. We're going to treat that as given value. I'm going to write a function here, and the function I'm going to write here, I'm going to say this is going to be print sorted, and this print sorted takes a list of people as a parameter, but I'm going to pass a comparator on a person as a second parameter, so comparator. So I'm going to pass two parameters to this function. We'll start with that. So I'm going to go ahead and call this function print sorted, and I'm going to send the people to it, but I got to send a comparator to this particular function. We'll come back to that in just a minute. So for this to work, I'm going to bring in, first of all, a couple of things. We're going to say import java.util.comparator, but I'm also, well, actually, we'll come back to that. So we have a comparator on our hand. Well, what do I do here? Comparator, let's start with that. A comparator on person, and I'm going to say comparator equals, and what do I do with this guy? Well, let's go ahead and say new comparator, and this is going to take a person as a parameter. And what do we normally do here? A public int compare to, and this is going to be person p1, and we're going to have a person p2, and this is going to become a return of, let's say, p1.getName dot compare to p2.getName dot, well, actually, that's it, right? So we're going to compare those two. Let's start with this little example here and see how this is going to work. Well, this is going to become a compare function, not a compare to function. And you can see in this case, we are using that. We'll take baby steps. So I want to go back and see what this is going to do. So we got a comparator coming in. So I'm going to say people.stream, and I'm going to say dot sorted using the comparator dot, let's say, for each system.out println, and I'm going to print that out. So when I run this code, you can see it's sorted based on the name of the people. Well, that got it working. It's not as evil anymore, but it's still verbose. We need to really make this better. Well, if you look at this code, we can see one thing going on already. We're using a single abstract method interface called the comparator. Well, we know one thing in Java 8, anywhere a single abstract method interface is being used, we can use a lambda expression instead. So notice, I'm going to remove the ceremony of here. The type is not needed. It can infer the type. I got rid of that. Put a little arrow right here, get rid of the remaining part of it, and remove, of course, the return as well. That's redundant. And we can remove quite a few things from the code, and we can reduce the code quite a bit, as you can see, by using a lambda instead of using an anonymous inner class. This also shows you that you can start on familiar ground and start refactoring your code. You don't have to make that leap and fall in the gap. You can take this gradually and say, I'm comfortable with this code in Java 5, Java 6, Java 7. Let me start refactoring this code one step at a time. There is absolutely nothing wrong with it. We just learn along the way, and then we'll be able to make that leap one day, but it's perfectly okay to take these baby steps along the way. So once we do, we got rid of the anonymous inner class and replaced it with the lambda expression. That's what we did right here. Well, that's great so far, but this code has a bit of a duplication, as you can see. I'm calling getName twice. Well, boy, that's ugly. I don't want to call getName twice. Well, you can start refactoring this with functions and such, and eventually what you're going to get into is you're going to get into replacing this with a comparable. You're going to say, in this case, a comparable. So I'm going to bring in a bunch of static methods and default methods from the comparator interface. So in other words, in Java 8, interfaces can not only have abstract methods, they can also have default methods and static methods. Now, at first sight, I really hated static methods when I saw them. I looked at them and said, gosh, this is ugly. And within an hour, I loved it. I can't remember any feature where I went from hate to love in an hour. Well, think about this for a minute. Say you're programming with collections, and when you're programming with collections, you want some utility functions. Where do you normally go? You go into the collections utility class. Well, you're programming with arrays, you want some utility functions. Where do you go? You go into arrays utility class. Well, that's what they started doing in Java 8 when they started writing. They had all these parallel utility classes, and somebody realized, why are we doing this? If we put all that in the interface itself, it removes all that burden. We know exactly where it is. So the utility methods or convenience methods are right with the interface. That really makes it so much more convenient to work with. So what I'm going to do here is, I'm going to come back to this code, and rather than going through all of that effort that we just saw here, I can simply say compare, and in this case, I'm going to start comparing based on values. So comparing, and what am I going to compare with? A person get name. So you can see in this case, I replaced it with comparing. Comparing is a static method that returns a comparator. So it's a static method on a comparator. It's a convenience method, a factory method, if you want to call it that, which will take a function, what you have in the parentheses is a function, and return to you a comparator back to you. Well, you can see in this case, nicely, we got that compared, as you can see. Well, that's great so far. And if I run this, you can see Bob is in the top, then comes Jill, then is Mark, and then there is Sarah. Well, that's great so far. But let's say we want to not compare based on the name, but I want to compare based on the age value. Well, just change this to age. How cool that is, isn't it? So I changed it to age, and you can see now it's sorted based on the age and not based on the name. You can see the 12-year-old is on the top, and the 64-year-old is on the bottom. Except there is one problem. I heard from Bob, and Bob is very upset. And Bob says, but why am I in the list below Sarah? There are two answers. The first answer is, Bob, you grow up, right? So the point is that you can just leave Bob where it is. But Bob is right. You want to really alphabetize the names if the ages are the same. So let's make Bob a little bit happy, and Sarah is more than willing for that. So let's go back here and say comparing, and then we'll say then comparing, and then we will say person, we'll say get name over here, and you can see in this case, if the ages are the same, then the comparison happens based on the name. Of course, if the ages are not the same, the comparison is just kept on the age itself. So you can see how you can make that a very nice composition of functions, even at that level. So the comparing becomes very, very charming. Likewise, you can call methods like reverse. Oh, one small detail, you probably realize this already. Comparing is a static method, but then comparing is a default method because it's already working on an instance of comparator. That's a default method. So this example shows you how we are able to leverage both static methods and default methods, which are part of Java 8, in a very meaningful way. So these comparisons become extremely charming and really beats to the punch any other effort we can do to try to write comparison and selective operations. Very, very highly expressive code, as you can see, that you can start implementing. There are some really complex reordering that you can do by using order by and reverse and so on. Depending on what context you place it, you can start reordering them very effectively, as you can see in this particular case. So that gives you an idea about how you can start comparing. And the benefit that you see up here is, of course, this is not intrusive. We did not have to touch our class person A. And second, you can also see that we did not modify the original collection that was given to us. We only transformed the sorted collections. The original collection is left intact, and you can see that's pretty safe as well. So that's again, and remember, we use the sorted method on the stream to perform this operation. So we saw quite a few features about streams already, so it's probably worth just reiterating some of those. First of all, streams are lazy. So streams are a lazy evaluation. They postpone evaluations until you actually need the results. Second is streams have a very nice wealth of operations you can perform, like filter and map and reduce and limit and sorted and so on. And you also have find first and methods like that. We also saw how when you are dealing with streams, you are able to take the streams and they could be infinite in size, it could be ordered, it could be unordered, it could be sorted. So there are different properties on streams that could be altered downstream, and so you can do all of these wonderful manipulations as well. Well, the last example I want to show you here is related to yet another feature, which is one of my favorite features that you can use with lambdas, which is called the execute around method pattern. So I want to show this execute around method pattern, but in order to show this pattern, I need to come up with a different example here, and I'm going to build it through Java 5, Java 7, and then show what's available in Java 8. So let's look at this example here real quick. I've got a class called resource, and if you look at this class resource, I've got a constructor for the resource. All that it's doing is it's printing, creating. I got an op1 and op2, which are simply printing those two text messages. I got a finalize method, which is really printing this message, external resource cleaned up. And then, of course, I've got the constructor being called here and these two methods. If I run this code, we can see whether the garbage collection kicks in. And clearly what you see here is the object was constructed, the operation 1 and 2 was called, but the object was not cleaned up. Well, did I misspell the finalize method? It turns out I did spell it correctly. So the question is, why did it not call this finalize method to clean up? Well, the reason, of course, we know is garbage collection in Java is automatic, but it is lazy. Garbage collection in Java is kind of like garbage collection in my neighborhood, right? It doesn't matter when I put the trash out, when it gets picked up is a completely different story. Well, the point really is, this is a really good example of a design flaw that every human who programs falls into at least once in their life, but usually many, many times. And that is bringing two independent concepts together. This is one of the biggest fallacies of programming, is we see this happen repeatedly every corner of programming we turn, including our own code. You take two things that are completely independent, but you put them together. And this is how code becomes complex and hard to maintain. Well, what are the two things here? One thing is we want to garbage collect memory. That's one idea. The other idea is we want to clean up external resources. Well, those two are completely different from each other. Memory cleanup is your business in memory management. Resource cleanup of external resources is a completely different orthogonal problem. And what they did incorrectly is they said automatic garbage collection will clean up memory, and while doing so, it will also trigger a function to collect external garbage, clean up external resources. That's a terrible idea. Now, the problem with this terrible idea is that when we are depending on memory cleanup, the memory cleanup, of course, could happen at any time the JVM decides to clean up the memory, but we cannot wait that long for external resources often. I'll share with you a personal experience I had. I do quite a bit of consulting work for organizations, and one organization called me and said, hey, why don't you come over, do a code review for us, and while you code review, maybe you can help find a bug we have been having and fighting for a while, and maybe you can help us fix it. And I was pretty curious and nervous. I mean, I want to go find a bug they've been fighting for a few months now. So I asked the manager, what's the bug? And he said, oh, go talk to the programmers. So I went and asked the programmers, different programmers, hey, I'm told I should be looking for a bug in your system. What kind of bug is it? Well, one programmer eventually nailed it. That programmer said, well, our code works fine most of the time. I said, oh, that's great. Can you tell me when it doesn't work? He said, of course, it doesn't work between 7:15 and 9 in the morning. I said, oh boy, every day. He said, no, only Monday through Friday. Right? It works fine on Saturday and Sunday. So I was pretty puzzled, like, wow, this is interesting. Why would it work on weekends but not on weekdays? Anyway, I had no clue. I said, I'll put that in the back of my mind. I will come back and visit it. And I was code reviewing, and when I came across one class, I stumbled upon the problem. Well, they had a finalize method implemented. That immediately triggered a few senses in me to look further. And when I looked into the finalize method, what I saw was, in the constructor of the class, they were actually going and fetching a JDBC connection from a connection pool. You know where this is going. In the finalize method, they were releasing that collection. And the minute I saw this, I'm like, oh gosh, I know what the problem is. Well, you have a lot of memory. Well, it turned out this was a portal application. Now you know why that's 7:15 to 9 in the morning. It was a portal application, company with 100,000 people working. You know what's happening between 7:15 and 9 in the morning? People come to work whether they want to or not, and they log into the portal whether they want to or not. And so there's a lot more activity on the portal application. And because there was a lot of memory, the JVM didn't want to do garbage collection. But on the other hand, the connections were being requested, not being released. Well, that exception was not being propagated properly, and as a result, we didn't really have a clue as to what was failing. And the minute I got a wind of it, the only thing I did that morning was I quietly changed that to a close method. That's all I did. And I came along and I said close, and I called the close method at the appropriate time, reran the code, and I asked them to go monitor the situation. Well, we were looking at the database connections being held, and before the change, and we looked at the database connection after the change, and what was increasing now was pretty flat, and of course the problem was immediately gone. So by lunchtime, that problem was gone after I were reviewing the code and found where the problem was. It was kind of interesting. After lunch, the manager comes back from his lunch, and as a person he should be very curious, he asked how are things, and the team said, oh, remember the problem we've been having for a few months? Well, we are glad to report it's been fixed. So he was very curious. He said, how did you guys fix it? And the team said, well, Venkat asked us to add a line of code, and we added a line of code, and the problem is gone. And then he said, well, what else did you do? It's like, no, nothing else. You just added this line of code, and the problem is gone. And there was a pause, and I heard him ask, if you only added one line of code, do we still need to pay him? So, yeah, absolutely. So the problem is we could have these kinds of problems in systems if we kind of don't have a clue where things go wrong. Well, unfortunately, though, there are two problems in this particular code. Let's identify what the problems are, and then we'll find the solutions to it. Well, the very first problem is, it is quite possible that as a programmer, I will forget to call the close method. That's reasonable, right? So I would forget to call close, and if I forget to call close, what happens? Well, back to square one. We don't have things released. It's even worse. It probably is not going to be released properly. We're in trouble. So the first problem is forgot to call it. Okay, that's fair. There is yet another problem. It's quite possible that the close method may never get called. Anybody has a clue why that is? That's correct. Thank you. Exception. So this code may have an exception, and when the code throws an exception, it never is going to come to the close method, and that's really bad. Well, so the question is, what about exception? Well, we got two problems, and I'm a firm believer in fixing only one problem at a time. And so let's forget the forget problem for a minute. Let's fix the exception problem. Well, what do I do about exception? Well, I could put a try block around here. I could move this into the try, and I could say finally over here, and then I could call the close method within the finally block. Well, now there's a good news, and the good news is no longer are we going to have the exception problem. But there is one small problem. Now we are dealing with not a forget, we're dealing with a forget plus plus, right? Because you may not only forget to call close, what are the chances you're going to forget to call the try and finally and close? And if I were to do this, that forgetfulness would be only 100% of the time, right? So that's not going to work. But the second problem, we solved one, but we made the other one worse. And now the code is more verbose as well, right? The code is a little pile of mess that we have to carry around. It doesn't look that great. So we got two more problems to solve on our hand. Let's again fix one problem at a time. Let's fix the problem of verbosity. Well, thankfully, there is a feature in Java 7, and the feature is called ARM, which stands for Automatic Resource Management. And this is a feature introduced in Java 7 called ARM, or Automatic Resource Management. And sometimes people call this as try with resource. That's another name for it. So what this says is, if your intention is to call a cleanup automatically, then we can facilitate the cleanup for you without you having to write the finally block. Well, in order to make use of this, you first have to go to the class, and you have to implement auto closable up here. So in this case, we implemented auto-closable. All that an auto-closable has is a public function called close. It's a tagging interface with a close method on it. So this requires the close method to be available. Well, great. Now that I implemented the close method right there, I'm going to come down and say try. And notice I'm going to wrap this construction with a try block. Well, now that I've wrapped it with a try block, I'm going to remove this try from here, and then I'm going to go back and get rid of the finally from here. So you can clearly see the code is a lot less verbose than it was a minute ago, and I will certainly, buy that. So I would say, okay, less verbose. I'm happy with that, right? So that's great. So now let's go back and run this, and you can see that the cleanup actually happens automatically. So when did the cleanup trigger in? Well, what this does is, the minute you leave the try block, this is actually a compiler facility. The minute the compiler, the Java compiler sees that you are using a try with resource, if you use Java P or tools like that and look at the bytecode, literally you will see the finally block in the bytecode. So instead of you and I writing this finally block, they write it for us, and they properly deal with nested tries and stuff like that. So they do a fairly good job doing this. So this is basically where when you leave this block, that finally block triggers in, and the finally calls the close, and as a result you can see that the cleanup happened properly. Yay, that's great, time to celebrate. Well, not so fast. What about the forgetfulness, right? So if I were capable of forgetting before, I could forget it now as well. So let's say I come along and I do not put the try at all, just like we did the first time, and I have the code like this. So you can see in this case, I do not have the try in the code. But here is my question. I did not put try, but as author of this class resource, the author did say auto-closable. So one wishful thinking on my part is the Java compiler can look at this and at least give me a warning to say, did you mean this, or did you really, really not want to clean up here? So my question to you is, A, it's going to give me an error or warning. B, it's not going to do anything. What do you think? It's not going to do anything. Well, those who are still thinking, there is a clue in this page you probably did not realize already, because you know the answer already. You should never ever trust a feature with the word management in its name, right? So, sorry, it's not going to do anything for you, and as a result you can see that didn't do a squat. So of course, what did you expect? So it would be nice if this actually did the work for us, but it didn't. So we are back to about square one with only a bit more ceremony than we wanted to. So yes, it's a good direction, but not, it's not gone further enough in my opinion. I really want a little bit more of this. Well, let's get a little wind of this from something that's been around in Java for quite a while, except that you and I could never use it for our own purpose. What I'm talking about is, you can say synchronized, if you remember, and I could say some object blah, and I could put code in here. Remember what that did, or what that does? Well, it says I'll acquire the lock for you, cross the memory barrier, enter the code block, and when I leave the code block dead or alive, I will release the lock for you automatically. That is a great idea from the point of view of cleaning up the locks, but you couldn't do that for something of your own purpose, either that or nothing. What we really want is an ability to use that feature, but for our own code, that would be really nice. Well, thanks to the Lambda expressions, we can actually do that today for our own code. How so? Let's fix that with one little effort at a time. So let's say I call the close right here, and you know this is the wrong code also because I shouldn't have called close here. I should have really called it within try and finally. And remember this forgetfulness that kind of keeps kicking in. What if there is no way to ever forget? What if there is only one way to do it, and that's the only way it'll work? That would be really nice. So how do I make that work? Well, the very first thing I'm going to do is I'm going to make the close method private. Well, what happens if I make the close method private? Well, the programmer who's using the class comes along, tries to call the close method. It says, oh, you cannot call close, it's private. And the programmer says, Okay, no worries, and walks away. That didn't really solve the problem. Okay, so that's a good first step. The next step is I'm going to make the constructor private as well. Now the programmer says, what gives? I can't really create an object. What do I do with this stuff now? Now we are forcing the programmer to do things in a certain way we want them to do. So what do? I'm going to come back here and say public static void use, and I created a static method called the use method. Well, you can see the constructor cannot be called. Well, op1 and op2 are instance methods. The user cannot call that also. So the user pretty much is left with the use method they can call, and they probably are wondering, what do I do with it? Well, we'll come back to that. So they can call the use method. Well, within the use method, I'm going to create a resource, as you can see right here, and I am going to call that try. Well, I'm the author of this class. I know about the pain of the resources, so I can't say that I forgot this myself, so that's not a problem. And then I put a finally block, and then within this, I'm going to say resource.close. Well, this is a static method in the class. I can call the private constructor. I can call the private close method, so not a problem. None of that would be a problem at all. We can certainly use that. Well, great. But then, of course, I can't really use a resource. I don't have it yet. We'll come back to that. But then, within the try block, I've created a resource, and I'm going to do something, and then when I'm done with it, I'll clean it up. So right here, I'll say block.accept, and I'm going to pass the resource to it. So if you look at that one-liner, no, don't worry about other stuff yet. We'll come back to it. We created a resource. We yielded that resource to this block and said, here you go, use it, be happy with it. And when you come back dead or alive, I'm going to clean up. So we took care of that logic here in this code. The only missing piece of the puzzle is the block. So I'm going to go back here and say .function.consumer. And in this case, I'm going to bring in a functional interface called the consumer interface. So I come back here and say use, and I'm going to say consumer resource, and I'm going to say resource. This is going to be block. And now you can see I've got a functional interface called consumer called block, and I call accept method on the consumer, give it a resource, and then when it comes back, I perform the cleanup. So now I can go back to the code here, and I can say, I've got a resource on my hand right here, and I'm going to go ahead and call the op1 and op2 methods on this particular resource. So now if I go back and run this, oops, wrong button. So if I go back and run this code right here, you can see in this case, it is calling the creating, and then you can see that it calls op1 and op2, but when we exit from the block of code, you can see how it automatically did the cleanup for us. Well, this is a pattern that was created back in the Smalltalk days, and this was documented by Ken Beck in his book called Smalltalk Best Practices, and this is called as a execute around method pattern. Well, that pattern heavily used Lambda expressions, but now that we can use Lambda expressions in Java, we can benefit from some of these wonderful patterns. This is called an execute around method pattern because we have a piece of code we want to execute, but around that code, we got a pre-op and a post-op we want to do. So this is kind of like I go to a rental car company, assuming it's a good company, they clean up the car before they rent it to me. I drive around town, they don't care where I go, hopefully. And then when I return it, they check for damages, more so for me than others. And the point is that there's a pre-op and a post-op, but I get to use it right in the middle. For that reason, this is also sometimes called as a lone pattern rather than being called as an execute around method pattern. You can use either of those terms. But this becomes a very nice pattern to use because we can take certain policies we want to implement in our code, and we can drive those policies into this method, and that can set up and initialize and conform to those policies, yield control back to our code. We can do our stuff, and then when we return back, that can clean up or do other checks on the policy when we are done with it. One of the applications I worked on, we had transactions that we had to run every single corner we turn, and we rolled this into a run-in transaction method, and that initializes the transaction with the proper settings, gives us the transaction object. We go do whatever stuff we want to. We return back. The code then checks for error conditions, logs them, rolls back if there was an error, otherwise commits it and moves on. So we didn't have to write that boilerplated code everywhere. That becomes a nice isolated code. We can start using it. If you look at the construct of the code on line number 22 to 25, this is a lot like the structure of the synchronized method I showed you a few minutes ago. You synchronized, you work on some context, you do some code, and you perform the cleanup when you're done with it, whatever that cleanup may be. That's what this pattern is really giving for you here, a very nice isolation of that. But of course, we are using Lambda expressions to do this in this particular case, and use method as its parameter is taking the Lambda expression that we are talking about, and that becomes a lot easier to work with in this particular context. As you can see, a very effective piece of code to write. So very lightweight syntax, very easy to write, and we are able to implement some of these wonderful logic around and implement our code as we would like to. Any questions or comments on this before we move on? Please, yes, please.
What's a good way to compose multiple of those closables into kind of one resource?
Like the use method itself or the streams? So one.
Instead of nesting it.
Got you. Oh, these guys. Oh, yeah. Okay. So these guys, well, so you have to deviate a little bit up from the command query separation pattern. What you could potentially do is you could go back to this code and say, I want these guys now to return a resource. And then you can say each of these methods, when they're done with it, they're going to return the current object itself. And the beauty is it doesn't have to be the current object. There could be a transformed object as well, as the context may be. And then what you can do is you can then come back here and say, well, I've got a resource on my hand. I can now say resource op1, and then I can just change that into a nice op2. So that is actually the cascade method pattern. I'm glad you asked that. And you can mix the cascade method pattern along with the pattern of execute around method itself. So you can nicely combine those two together, as you can see right there, that works. So yeah, thanks. So you can do a nice cascade method pattern. Some people call this cascade method pattern. Others call this a train wreck pattern. Both works not just fine. So you can actually cascade it. But to cascade it, you would have to change the contract a little bit. Either they return the this or another transformed object or an interface, and then you can start building on top of it. That can be a very nice, powerful pattern to follow. Yeah, absolutely. You can certainly do that as well. So that works really well.
No, I mean if you have two different resources.
Sorry. So anyway, strike this. So if you have two different resources, you can nest them. So there's nothing that says you cannot nest them. So absolutely you can nest them. The code can get a little ugly. So you want to modularize and refactor it to the extent where maybe you would just nest them, but get the resources, pass them to another function, and then that function can do the job. When you return from the function, this can then do the cleanup and give it back to you. So you can do the nesting. If the combination is a lot more common, the use itself internally could take multiple chain of parameters, initialize a group of objects and return to them. So there's a bit of a combination of things you can do based on the particular need in the design. You could do that as well. Any other questions or comments? Yeah, please.
How will you go about testing it?
How do you go about testing it? That's what the users are for, right? Okay, so the way you would test it is, again, you would start testing the individual methods one at a time. And then what you can also do is, depending on your specific needs, you can also do a fairly good amount of testing by effectively mocking some of these functions as well. And in this case, you could probably do a very simple mock, like a Mockito spy would probably be your best bet, because it can spy away what you don't want to use and only mock away those little methods. So you probably can do a combination of testing those methods in isolation, and then maybe spy away a few methods and test it as well. So once you get down to it, it's not too hard to figure out how to get around to test it. I'm really excited to see these testing questions. That's awesome. Yes, please. Is there a performance impact in terms of transformation? The answer to that question is not as significant, and the reason simply is what Java does is something phenomenal. So when you are, let's say you have 7 transformations. So you have this particular collection, map. Java does not collect collection intermediately. What instead Java does is it starts with the original collection. It doesn't do any work at all, but grabs them all into memory as functions. It does not even touch the data. When you trigger the final computation, it goes from the source collection into one shot into destination collection, and it performs all these computations in memory and sets it. It doesn't create garbage in between. It doesn't create collections in between. So it's pretty darn efficient because of the laziness. So as a result, you get a fairly good performance because of that reason, as compared to where we naively would be going from a collection to a collection to a collection, then we would suffer through performance. But they've done a fairly good job in identifying that and wrapping through, so we don't lose on the performance for that reason. Any other questions? Yes, please. This is about the execute-around method pattern? Okay, so how would you use inheritance, like where the resource is inheriting from another class, for example? Oh, yes, yes. Okay. Got you, got you. So you can actually, so those methods you are calling would be polymorphic based on the virtual method. So if you have an inheritance, you're not calling a static method, you're calling an instance method. So in other words, when you see person colon get name, this is a shortcut for person arrow person dot get name. So, and of course, we know that this is polymorphic, so that will work. So if it's a static method, we will be in trouble, but it's an instance method, it will resolve properly, so that shouldn't be a problem. Yeah, so if you're interested in downloading the code examples I showed you here, you're most welcome to download them from my website. They will be there anytime you want to. Just go there and search for the topic, you'll be able to. I hope you found that useful. Thank you for your time.